We'll start the webinar in just a few seconds. We'll just give people some time to join. All right, so we'll get going. So hi, everyone. Thanks for taking the time to join us today. We'll be starting the webinar in just a few moments. My name is Tina Fabiano, and I'm on the enDAQ Marketing and Engagement team. In a minute, Steve Hanley, our Vice President of Product, will be presenting today's webinar and Q&A session on Get Started with Python, why and how mechanical engineers should make the switch. During the webinar, Steve will give a brief overview of Python and why it may be right for you, explain how you can download Python and the environments in which you can code. Then he'll walk you through an example script and we'll finish up with a few questions and give you some helpful resources. In addition to Steve, we also have David Stokes, Connor Flanagan, Becker Alcati, and Sam Ragusa with us today as panelists. They're all on the software team at enDAQ and are incredibly knowledgeable on this subject, so we're excited to have them with us to answer your questions. This is a 45-minute session. As you're watching the webinar, don't hesitate to use the question and answer button labeled as Q&A right at the bottom of the screen. Steve will try to answer a few questions at the end of each section, and the software team will be able to type some answers in real time. Then the team will answer any other questions at the end of the webinar. We'll also have a poll question for you to answer, and at the very end, we'll launch a post-webinar survey. We'd love to have your feedback so we can make sure we're providing you with relevant resources around this topic, and so we can continue to improve our content. We're really excited to be running this webinar today, answering your questions, and making the case for why you should use Python to conduct your analysis. So with all that, I'm happy to introduce Steve Hanley, who'll be taking it from here.
Thank you, Tina. Yeah, we're very excited and admittedly a little nervous to give this webinar. Nervous because there's a few hundred people of you, so it's the most we've had on a live webinar, but we're excited because there's clearly a lot of interest in this topic and one we think we're uniquely positioned to help by generating the content we're generating today and going through, but also by directly helping release some Python packages to help folks like yourself analyze data and get to the heart of the matter and know what to do with the data. So as Tina said, I'm joined by 4 of our software engineers here. They'll help answer questions as we go. These guys helped get me into Python a few years ago, and they keep showing me all the cool things Python can do on a daily basis. So we have a lot to cover today. As Tina just said, we only have 45 minutes, so we're going to go through it relatively quickly. I'm going to start a poll question now to kind of get everyone's blood flowing a little bit. I'm just going to ask here, what type of engineer are you? Or do you have any familiarity with MATLAB? What is it? Do you have any familiarity with Python? So that poll is launched. I don't know if anyone can see that and can answer some of these questions. That'll help tailor how we go through this today. So we'll give you guys another moment. All right. So I'll end the poll, I'll share the results. So if you see here, we got a lot of you mechanical engineers, which is good. That's what the title of the topic is. And you see that there's a little familiarity with Python, which is good. And people have some familiarity with MATLAB as well. And there's a little bit more experience in the MATLAB side for this audience. So that's to be expected and good. So let's get into it. All right. Why should we be learning Python? Well, there's a variety of reasons, but here are some high-level ones. One is it's very, very popular. I'm not one for following the crowd, but in the case of programming language, popularity is helpful. It's helpful. You can search online and find a lot of resources to teach, to become self-taught, which I've done. I've never taken a class, but I've learned a fair bit just by Googling. And then also with all these resources online and examples, you can hack together some analysis routines that can be pretty advanced, but by combining some examples that you find online. The other benefit of the popularity, especially in the case of Python, which is open source, is as more people start using Python, more people can contribute to it. And so the functionality and the performance of Python can improve. And so you get this kind of reinforcing loop. More people join, it becomes more advanced and more capable, and then it attracts more people. One thing I want to call out in this plot on the left of the popularity over time is in the late 2000s, MATLAB was starting to gain a little momentum and Python was actually coming down a bit. This might be well correlated to when there was some interest in data science, and MATLAB was well positioned to be the de facto place that people analyze data. And that maybe started to happen in the late 2010 timeframe. But then the trends reversed around 2015. And since then, anyone that's doing data science besides mechanical engineers are pretty much using Python. This is coincidentally when pandas starts gaining in popularity, is around 2015. So now it's time the mechanical engineers follow suit. Python's free. If you come from MATLAB, you're used to spending $2,000 a year per user, and that's just for the base package. Then you have to pay for the toolboxes. I'd always pay for the signal processing toolbox, which is another $1,000 per year. And we only at our company had one computer that had it. So I had to keep fighting this guy, Jeff, to get access to that computer. That was a pain. In Python, it's free. And so I can get these advanced packages and libraries without paying anything. It's also free in terms of the freedom and flexibility. It can be a little overwhelming, and we'll see that today where there's so many different ways to download Python, use Python, but in MATLAB, there's just really one option. But the benefit is that once you kind of get used to that, you can find something very unique to you that helps you do the functions and the capabilities that you need. Last reason is Python can do a lot. It can excel at data science, which we're going to go through today, analyzing some vibration data. But Python can do a lot more. A lot of websites, including Reddit and Instagram, are built on Python. You can write very advanced software programs in Python. You can do web scraping and interfacing with web APIs in Python. All that can't really be done in MATLAB. So if you learn Python for your job, you might also find some hobbies that you can also take to benefit from Python. I actually came in to start playing with Python back in 2015 and 16 to do some algorithmic trading, which was kind of fun, but a little bit of a black hole. All right, so comparing Python to MATLAB, there's a lot of content that gives good comparisons between MATLAB and Python. I actually wrote a blog in 2016 to compare the speed between Python and MATLAB for doing some simple vibration analysis. I was loading a file, plotting it, and then generating an FFT. So I timed the two. And I was used to MATLAB, so my first attempt showed MATLAB greatly outperformed Python. But then I quickly had the help of some of the panelists here that I'm joined by, as well as the audience at large. People commented on my blog. And within a week or two, I had updated the blog with using the right packages, including pandas and some FFT library. And I was actually able to beat MATLAB's performance. And if you look online, you'll be able to find similar tests and results that people have generated. You just need to use the right library. Once you find that library, you're likely to be able to outperform MATLAB. And again, it's free, it's readable, it's better in a lot of ways. Now, there are some libraries that MATLAB has that Python doesn't have an equivalent for yet, one of which is Simulink. I don't think there's anything readily available in Python. But again, that might change in the next few years. So just be on the lookout for all the right libraries to be using for your particular job. Another note I want to make is if a lot of you are coming from MATLAB, there are almost one-to-one conversions to go from MATLAB code to Python code if it's relatively straightforward. As you see in this image here that was generated by a company called enDAQ. They have a lot of good online material as well to check out. But if you have been using MATLAB for 10, 20 years and you've built out a whole library of scripts, it would definitely be a chore to convert it to Python. But if you guys are relative casual MATLAB users or not even MATLAB users, all looking to start, Python can definitely do what you do in MATLAB and arguably do it better. Okay, last thing before I start actually getting into some demonstration, which is I just want to compare writing code in Python to using a software GUI. Many of you on this webinar likely downloaded our vibration data toolbox, which we partnered with Tom Irvine for. And that thing's great. It's a really good graphical user interface to do some vibration analysis, but it has some limitations. One of which is because it's a GUI, it only gives me the options that are explicitly available in buttons. And that means that if I want to customize something, I can't. And that used to really frustrate me. Even if I wanted to just change the colors in a plot, I couldn't do it. I had to export the data and then go do it somewhere else. When you're writing code, there's really no limit to the customization that you can add. And this was important to me when we were building out enDAQ Cloud. We wanted the report generation to be customized with code so that there really was no limit. And that's, I think, a major selling point to using code as opposed to a GUI. Another one is if you're doing a batch routine. For me, in the end, the vibration data toolbox, I was oftentimes generating a power spectral density and a shock response spectrum. I was clicking the same buttons in the same order every time, and it was tedious. And if I wanted to just run the same routine on a new data set, I can do that with code. You can't necessarily do that with a GUI. And last but not least, it's very easy to collaborate when you're writing code. I can't tell you how many times we've worked with customers, even internally, to help them debug why they're having different issues with how they're analyzing the data. And I need to almost do a screen share with them and watch the buttons as they click them and say, no, you should have done it this way. Whereas if they just shared their code, I could very easily say, oh, you need to reorganize this or pass this parameter. And so you can collaborate much more easily when you're sharing code, and especially with Jupyter notebooks that you'll see in a moment. So with that, let's get into actually getting started in Python. So the first thing to get started is you have to download it. For everyone in this webinar, I'd encourage you to just download Anaconda's individual edition. It's totally free. It comes complete with a bunch of libraries that you'd use in data analysis, and it comes with some IDEs, some environments for writing code. So there's just one download and then you get started. I did have to call out though that they do want you to pay for their commercial version if you're what's called a heavy commercial user. I don't think anyone in this webinar would be classified as a heavy commercial user. That's somebody who's mirroring their code repository with Anaconda's. So you're always up to date with the latest packages. You can do that just individually and manually, but if you were to mirror it, they want you to pay the nominal fee of $15 a month. Again, I don't think anyone on this would classify as a heavy commercial user, but pay attention if you think you are. Now there is some benefits to paying that, where you get always the updated version. I also had a colleague here that one time expressed concern with Python because he said there was no company to maintain it for me. And he was worried that it would just stop running and wouldn't be supported. I kind of smiled, and I'm smiling now because there's millions and millions of people using Python, so it's not just going to stop. But if that is a concern of yours, you may find some solace in the fact that there's another commercial entity out there that's helping maintain it. They also can provide some benefit of letting you collaborate on code with colleagues. If you want to go a different route, go straight to the source, you can. You just go to python.org, download Python. To me, it was always confusing, still a little confusing because it doesn't come with all the packages I need and I have to go find them. And you can try it out, and that's totally free and open. But I think for everyone on this call, go to Anaconda, the individual edition, and you'll be up and running. So with that, let's actually get into showing some stuff and writing some code. Here is Spider. So if you're from MATLAB, this is going to look somewhat familiar. You have on the left your code that you're writing. You have over here a variable explorer and your plots, and then you have a console to write your code. So for example, I could say x equals 2, and now I see that in my variable explorer, y equals x divided by 5. I see another variable, it's a float, not an integer. And this, I think for a lot of you that are coming from MATLAB, this is going to look familiar and be nice. I can run this code. This is just loading a file. And here's a load of the file. It generated a few plots, and there's some variables here that populated. My plots are in line here, so I can kind of poke around here. I don't like this look because these aren't very interactive. There are ways to pop out the plots and make them interactive, but I think I'll show you something that's, in my opinion, better for doing data analysis in a moment. One thing is some of the plots I opened, I generated as HTML files. You see, I saved it here as an HTML, and I can open this in a web browser. So this may be one way you can get some interactivity. The nice thing too with these plots is it's in a web browser. I don't need to be, I don't have to have Python running or installed to be able to interface and interact with these plots. And so I could send this to a colleague without MATLAB. And when I've shown some people here, or without Python, when I've shown some folks here, they really fallen in love with the ease of use of some of these figures that you can generate. Is there anything else I should show in Spider? Again, we're going through this relatively quickly. I'm just trying to show that this is an environment that you can write code and it would be familiar to you if you're a MATLAB user. This is included in Anaconda. So you just open Spider once it's downloaded, and you have an interface that hopefully is intuitive if you're used to that. Another one I'm going to show you is called Jupyter Notebooks, and then Jupyter Lab. So real high level, a Jupyter Notebook ties your code to the output. So you see here, I have some lines of code, or some cells rather, and then the output is right below that. And what's nice is that interactivity now is embedded. The first time I saw notebooks, I really fell in love, because when you're doing data analysis, you tend to have an iterative process, right? You generate a plot, you look at the results, you then maybe change something, and you have that all tied together in a notebook really nicely. The other thing that's nice about a notebook is you have these headers, and I'll show you in the Colab link that we'll go through in a minute. They're markdown text. I can add a list. I can bold stuff. You can do all that just right here in the notebook, and it's tied to the code. So it gets to a point that as you're going through, you're explaining what you're doing, you're seeing the outputs, you're maybe drawing some conclusions, and you're writing that right in here. You can export this as a PDF document or as an HTML. So somebody could get that interactivity, again, without Python. Or if you can share this now with a colleague, you can download it as a notebook file that then in Python they can open and run and modify. So I think this environment is really helpful for exploring data that tends to have an iterative process. You kind of need to explore and try things out. Now, these are notebooks. The other option I'm going to show you is called Jupyter Lab. So it's just oops, I need to do this lab. This is what Jupyter came out. They came out with Notebook originally, and then they built this IDE, this environment around notebooks a couple of years ago. I'm not sure exactly when they came out. And so this is a kind of a hybrid between that notebook look and feel and the environment that you may be used to. So as this is loading, you see here, you have the notebook here, and I can kind of reorganize in a very modular manner to compare different notebooks at a time. I also have the ability here to have a variable explorer, and I have this module down here as well that I can try things out and just do quick executions. I can do fig.show. So you get a little bit of the benefit of maybe what you're used to in an environment while still getting, oh, did I not save fig? Oh, I need to run this. Let's do this run. I deleted fig. There we go. And so this is a nice hybrid, I think, for folks that like the environment, but like Jupyter Notebooks, you kind of get a bit of both. And you can switch, as you saw, between the notebook view and the lab view. You see these, the variable explorer is nice too. I can see my array, and I don't have to print it every time like I may in a notebook. Well, with that, let's get actually into a real pretty deep dive example. And I'm going to show some code as we go through this Colab example. I think Tina sent out the link. There's a link also on my blog. And so what's nice about Colab is it's in the cloud and it's like a Google Doc. And so that's what I'm in here. There's some benefits. You can share like a Google Doc, your document with somebody else. They can just log into Google and start collaborating with you. There's also the benefit where I can run this on my work computer that's a Windows machine, go home, open it in a Mac, and maybe on the couch, try some things out on a tablet. That's all the same file that's hosted in the cloud. It's really nice. It has the same interface as the Jupyter Notebook in the sense that there's cells of code and cells of text, and the outputs are tied to the code that you see here. But there's a couple downsides to Colab. One is it's in the cloud, so you have to explicitly upload data to the cloud, which I show you here in this example. You could run this cell. You could also here on the left, just right click and hit upload. I'm going to cancel the upload. I have also some examples here that I've already preloaded. So if you're using a bunch of local data that you're trying to analyze, Google Colab's probably not going to be the right place because you have to upload it every time. But if your data is already hosted in the cloud, like if you're accessing it from an API like the enDAQ cloud or someone else, it can be very easy. The other downside of it being in the cloud is that the runtime has to be supported by Google. And so if you leave it idling for a little while, you may get cut out and you'll lose your local variables. But you can try out Colab, and the interface is going to be very similar to Jupyter, so which you can run locally. So now let's get into this example. So the first thing I'm going to show you here is I'm making a list of these various file names. And again, this data is already public. You can play with them. They're pretty interesting data sets. But the first thing I want to call out is that this list is indexed with the first element is actually index of 0. That was really counterintuitive to me when I started. MATLAB starts with the first index being 1. The software engineers here can give a better answer than I, but the reason it starts at 0, I think, has something to do with the memory allocation where you point, but the first instance is actually 0. So if you get past that little nuance, I think you'll find that it's pretty straightforward to use. So right now I've just created a list, and then I've defined my file name as index of 2, which is actually the third element, and I can just print it here by doing Shift Enter, and I see it's the bearing data, which I wrote about in a recent blog and webinar. So now here, I'm explaining that you need to install various libraries in Python to use them. If you're coming from MATLAB, you're used to everything in one, which has some benefits, but there's over 300,000, I think, libraries on PyPy that you can install. So it starts to really explode the functionality when you're able to share different libraries. Now in Anaconda, so if you download Anaconda, a lot of these libraries will come already pre-installed. Colab, same thing. A lot of these libraries come pre-installed, so you won't need to explicitly install them. But this would be how you do it. You do pip install and then the library name. So when we release our library in the coming weeks, you'll be able to do pip install enDAQ and then have this new library and the new functionality within it to use. You also can upgrade libraries. You know, these libraries are being updated daily. So here I'm upgrading Plotly to use the most recent version because the one that's built into Colab has some limitations in this environment. Once you've installed your libraries, which you only really need to do once, unless you're upgrading them, you need to import them though every time. So every time you run Python code, you need to import your specific modules you'll be using. Here I'm importing pandas, which I'll show you some examples. They have data frames, which are really nice interface to tables of data. But I said import pandas as PD, which then lets me every time I write PD dot is the equivalent of writing pandas dot. So I do that with NumPy as well. This is for matrix operations. I'll have a lot of functionality that's built into MATLAB. Then there's these two plotting libraries I'm using, and I'll give you a comparison between the two in a minute. And then from SciPy, importing a library, their signal processing library. So I'm saying from SciPy import signal. So you can import parts of a library, the whole thing, and you can abbreviate them as you go. So now I've imported these libraries, and I can start writing some code. So first off, I'm going to import this, what's called the data frame. So here's the data frame. I just did pandas.readcsv and passed in the file location. You can pass in the local file location if you're running locally or an online one, and you get the same result. You don't have to use CSVs. We all default to it, but There's better file formats out there like Pickle and HDF5 and the Pandas supports, but I know we all like CSV, so we'll use CSV in this example. So this data set I've used has the first column being time, and the other 4 are acceleration channels. So this is going to be common for a lot of your data sets. You'll have one being time or frequency or some other index, and then there's the actual data, the values. And one thing that's really nice about Pandas is I can explicitly say, treat time differently than the other values, the other columns. And so here I'm saying, set the index to be the first column name, and I can show you what, so df.columns is going to be a list of the column headers. And so if I do df.columns 0, it's the very first column. So here I'm saying, load in my data frame and then set the first column to be equal to, or set the index to be equal to the first column. And here's my result. And you see now time seems to be treated a little differently. And what's the benefit of that? Well, one of the many benefits is indexing. So let's say I want to get all the values between time of 1 and 1.1 seconds. I just I'm going to zoom in a bit. I don't know if I need to. Write out df and then 1 colon to 1.1 and do shift enter. And now you see my result is only the values that fall in that range. I can also just go colon 1.1 and it will just give me all the results up to 1.1 seconds. So there's some nice things there. There's also in data frames, I can do filtering pretty easily. So let's say I only want to see results where this particular column, fault 014, is greater than 0.2 Gs for whatever reason. That filter is pretty easy to apply, and now I see the results and they're all here. There's a lot of other benefits in data frames, but those 2 that I just showed you are some of the basic ones. Easy indexing and easy filtering of the results. But now let's do some sweet analysis. Here I'm explaining the analysis I'm doing. You'll notice that I have some nice equations. This is generated in Markdown text. So again, that's a benefit of Colab and Jupyter Notebooks is you have the ability to richly describe what you're going to do all in line with the results. So here I'm actually showing there's a built-in function in Pandas called describe. And so when I do that, I get all these metrics that are pretty useful. How many values are in that, what the mean, the max, the standard deviation. Then there's percentiles. So the 50th percentile would be the median. And you have that in just one line of code. There's also these other built-in functions like max. And I see now the results, all the max values. .std is going to be the standard deviation. There's min. There's a lot of things that are pretty easy to do. I can do quintile, and I think I just passed in 0.25. So this is going to be the, oh, I can't spell quintile. I don't want to figure out how to spell that right now. Let's see if I can. There we go. Quantile, not quintile. And there's the result. Okay, so here I'm going to be getting the absolute value. I'm trying to get the peak of every channel. So I do df.absolute. So now every value is an absolute value, and then I'm getting the maximum of that. Let me just show you what this result looks like. This is going to be a series where I see fault 021. This is the corresponding value. So I did that for the peak, the standard deviation, which is equivalent of RMS, and then the crest factor is the ratio of the 2. Then I merge them back together into a table, and then I define the column headers. And here I have a nice summary of my data. But you guys want to do some plots, and I've already gone 30 minutes, so I need to start racing through the plots. First thing is I can plot data that's in a data frame with the simple line of code of just df.plot or whatever my variable is called, and then I get this plot. If you are used to MATLAB and you want to change X labels and Y labels, add a title, turn the grid line on, you can do that here, and it's going to have actually a very similar interface as MATLAB will, the API. You can save the figure and then show it. Now the downside is this is matplotlib, which these figures are images. They're not very interactive. There are ways to make them somewhat interactive in the notebook view, but it's pretty cumbersome. And so there's another library called Plotly, which I've fallen in love with, and I'm not alone. It's gaining a lot of popularity. I link here to some good examples that they have online to use Plotly. Now, the only downside of Plotly, though, is it can't necessarily plot millions of data points with that Matplotlib didn't have any problem with. That being said, I've always maintained that plotting millions of data points is kind of a waste of time. You need to kind of downsample a little bit and summarize and find areas of interest. And then once you found an area of interest, you can plot all that data here. So I'm going to show another example that's built into pandas, which is their rolling function. So here, let's say I want to segment my file. There's 120,000 data points, and I want to only get the maximum of 100 segments. So here I said I want 100 steps. And then this next line of code, I'm saying, okay, my whole length of my data frame is this value, and I'll show you. It was 120,000 if we remember. I'll just do df.shape. The shape is the length and then the width across. So when I get the first instance, remember it's 0, that's going to be the length. And so now I'm saying I want the whole shape, the length divided by the number of steps, and that equals n. And if you see here, if I hover with my mouse, you actually can get this variable explorer in Colab, which is pretty nice. I think I sometimes forget that you can just hover to see the value. You don't have to always print it. But in any case, there's a built-in function in pandas to do this rolling, and I'll do, so if I go like this, I'm going to get an array or a data frame that's the same length as the original, so 120,000 samples, but for every sample, it's been calculating the maximum across the previous n values. And so if I plot all these, I'm still plotting 120,000 data points. So here I'm explicitly saying plot every nth value. And then that's what this result is. And you see it's only 100 lines or 100 instances. So now I can make this other figure. And this is a Plotly figure. Again, it's very dynamic in this view. I can zoom around. I can turn on and off different channels just by clicking in the legend. I can export this as an HTML file, which I'd shown before. And you see that over here, and I can download this. Okay, I got to keep going. Another example will be showing the rolling RMS. So it's very similar to doing the rolling peak. Instead of saying rolling.max, I'm going to do rolling.standard deviation. I'm also going to add another little mix here where I'm going to define my theme differently. So there's all these built-in themes in Plotly. So I like dark plots. So I'm going to say I want the template to use Plotly dark. And here's the result. I gave a link up here to their website that have, again, they have really, really good documentation, really good examples. So you see all the different themes that are available. You can also write your own theme and then use that. So I think that's nice. Now, let's do another bit of code to find the peak and plot the time series around the peak. So this first bit, I'll show you this, where, remember I showed you dataframe.max found the values across the whole column. If I pass in max and then axis equals 1, it's going to find the maximum value per row. So once I've done that, I can say, okay, here's the maximum across all the rows. Now find me the time at which the max occurs in that max per row. So now I know the time of 3.7 seconds is when this maximum value occurs. And so at these few bits of code, I'm saying, all right, I know the time the maximum is, and I want to segment my data frame to plot from this peak time minus 500 data points and then plus 500 data points. And now what does that figure look like? And so this is the real time series data. I changed the theme again. I did Plotly white, and away you go. Okay, I got a couple more minutes left before I open up to questions. This is one more thing I really want to make sure I show you all, which is a function in Python. If you're used to MATLAB, when you define a function, you have to close a function with end or with a bracket, I forget exactly. Here, my function is defined, but based upon indentation. So you see here, here's my definition of the function, get PSD. Here's the parameters I'm passing in. And then everything that's inside this function is indented. And that's how Python knows it's part of the function. And then I'm returning the output. There's two things I'm going to show. One is that the parameters to use this function, I have one that is just doesn't have a name to it necessarily or a default value. These other two have default values. So I say bin width equals 1 and window equals Hanning. What this lets me do, if I run this, so I've declared my function, I can get the result of the power spectral density just by passing in the data frame of the time series. And it's going to default with a 1 hertz bin width. You see frequency of 0, 1, 2, 3. But if I do bin width, equals 4, for example, now I have my frequency steps are every 4 hertz. And I think this is really nice to get these default values anyways. So this is my function, you pass in the data frame, a couple other parameters, and you get an output of the result. And this is using SciPy's Welch function, which there's a MATLAB equivalent to you may be used to. So once I have the data frame output, I can plot it. And here's a nice clean power spectral density of that data. And again, I can save this as an HTML, which I did. I could download this. I also exported, if you noticed, the PSD result to CSV. And so I could export that as well. Okay. Once I have a power spectral density, I can get the cumulative RMS from that by this equation. So I defined another function, and there's one thing I want to highlight, which is something that's a little bit weird if you're used to MATLAB, which is getting the square root. So raising something, so let's say I have 2 and I just want to raise it to the 16th. If I do 2 raised to the 16th, the result isn't what I expect, because that's, I forget, Connor and Dave, you guys will know what this actually is. I'm not sure what that even does in Python. But in Python, in order to do an exponent, you need to do 2 asterisks, like 2 multiplications. And this will be 2 raised to the 16th. So if I want to get the square root, it's 2 multiple dot by 0.15, and now that's the square root of 2. So here in this function, I'm getting, I'm multiplying the power spectral density by the frequency bin width, then I'm getting the cumulative sum, and then I'm getting the square root of the cumulative sum. And then I generate a plot. I didn't even highlight before, but generating a plot in Plotly is really, really easy. It's just XP, which is their Plotly Express, and then they have Plotly line, they have scatter, they have bar charts, and then you just pass in the data frame and you get the plot back. I did, change some parameters like the title and the x-axis title and stuff, but I just want to highlight that. And here is, oh, what did I do? Oh, I didn't call this. There's a cumulative RMS. Okay, I don't know if I have time really to go through the discrete Fourier transform, but here is some code on how to do that. Is there anything else I want to show? Oh, I have another function in here that you can kind of walk through, which is finding the moving frequency over time. This data set isn't all that interesting, but you can, I have a for loop here, which I wanted to include somewhere. So this may look familiar, for I in range of 0 length. The first one is the start, the second parameter is the end, and then here's your step. That's how you can do a for loop. Another example is, remember my file names? This was a list. If I want to loop through those, I can say for F in file names, which I think is pretty intuitive, and then print F. And run that. So it gets the same result. I'm looping through every time. So that's you should check out. There's a lot of content online on for loops in Python, but I just wanted to have one example to show you. And here's now the result of running that function. Okay, Tina, I flew through that in 40 minutes. I'm sure there's some questions. What do we got?
Yes, got a couple of questions for you. So one of them is, will the enDAQ Python library allow you to read native IDE files?
Yeah, that's a great question. We actually have an open library right now. It's IDLib that I encourage you to check out. But there'll be enDAQ.ide, which will include some functions to really easily get. If you remember in this example up here, I really like, and I'm not alone, the world really likes these data frames. And so there's going to be a function in enDAQ.ide to get out a data frame of your acceleration data or your temperature data or what have you. And then once you have it in this form, there's tons of online material about how to analyze that. So that's a good question.
All right, so another question that we have is, would you recommend Python for a first course in numerical methods for mechanical engineers, root finding algorithm, et cetera? Do textbooks exist for this sort of course using Python?
Yeah, I was talking to our vice president of engineering here at MeDay, and he was commenting that MATLAB does a really good job. If you've got a mechanical engineering degree, you probably took a course in college that went through MATLAB. And I don't know if they're doing that as much in Python. I'm sure they're starting to, but there has to be a lot of material out there in textbooks on Python. Again, I personally just like diving into something and trying it out. I'm not really one to sit through a course, but I'm different maybe. And you can do either though. There's tons of courses. And if I go back here to our presentation, I linked to some, and in the blog, we linked to some as well. There's Data Camp. Data Camp goes through a real course. Real Python has a course that you go through with specific modules. And what's nice is that it's interactive course. So you actually have a Python console that you're able to write code and it checks the output as opposed to just reading a textbook. So I'd encourage you to check those out. Some of those are free, but some you do have to pay for.
All right, so another question is, will the enDAQ library include a function to convert acceleration to velocity to displacement and vice versa?
I love these questions. These are, you might have seeded these, Tina, I'm not sure, but that's a great question. Yes, that's one of the built-in ones. There'll be an enDAQ.calc is to double integrate into velocity and displacement. And what I should mention too is that won't be, you won't have to have data from our devices in order to benefit from that function that will be in there. So we're really excited to introduce that. There's ways to do integrations in Python, obviously, and we're using that. But our function is going to be doing the filtering and the 2-key window before every integration. And there's some other smarts there. So that will be a really helpful tool and function for people. And one line of code, get my velocity equals enDAQ.calc.integrate, and then you pass it the acceleration data.
We did have a question more specifically about any books to get started with Python, or would you just recommend online resources?
I didn't read any books. I'm not sure if any of our software engineers went through a specific course and a textbook that they can recommend. I would, again, Python is remarkably popular, so I'm sure there's tons of blogs ranking the best books for Python. So I personally can't recommend any, but I'm sure there are many out there.
This is for one of the, I believe, one of the programs or slides you're using. It says, I missed the data name for file name 2. Which vibration type file name index 2 belongs to?
Okay. So if I come up here are my example files. Remember, index of 2 is really the third. And I can always check that by saying file names and just print the index of 2. It's this bearing data, and I link, it's from this blog. If you read this blog, this is the data I went through in this blog. I can very quickly give you an explanation of some of these other data sets. Here's one from a customer. It's pretty cool, where it's on some surgical instrument that's vibrating at a very specific frequency. It's kind of interesting. Here is some data from a rocket. We actually have a blog on that one too. The motorcycle crash test is in the blog for shock response spectrums, if you've read that one. The calibration shake is pretty good. That's when we calibrate our devices, we shake it at 100 hertz and 150 hertz. So you get 2 areas, and I can just maybe quickly show you that one. I should do here. I'll set my file name to equal 4, which is the calibration shake. Then up here, I'm just going to do run all after. Now all these cells are being run. Oh, I indexed. There we go. And here is the output from that. So you see here, there's 100 hertz and 150 hertz. And I think you'll see that in my last plot, which is showing, well, here's a power spectral density. You see one at 100 hertz and 150. And then when my last function, I'm plotting the peak frequency over time. So you see that. So there's some interesting data sets, but that's a good question. The one that I went through for the most part of this webinar was from bearing data.
Do we have time for 2 more questions?
Yeah.
All right. There's a follow-up to the acceleration question. Will that function also include filtering or cutoff options?
Yes, I don't know if I want to put Becker on the spot. If you want, Becker, you can turn your camera on to answer this, but yes, it will have default settings for the filter cutoff, as well as the 2-key window, the taper. And if you remember from my example up here when I was doing the PSD, I think the interface is, there's the default settings, so you don't have to explicitly define them, but you can change them if you'd like. So you could just throw it the acceleration data and get an output, or you could play around with, I want a filter starting at 2 hertz or 1 hertz, and I want to have a 2-key window of 0.95 or 0.8 to taper the beginning and end more aggressively. So that's a good question. That's an exciting function. And remember, I don't know if you mentioned that at the beginning, Tina, but we're going to host another webinar in exactly 1 month to go through this new library, which will include that function and go through some good examples.
Will this be useful for analyzing shock data from barge tests, et cetera?
Yes, for sure. One of the things that is not very easy out of the gate is the shock response spectrum. The power spectral density, there's a built-in function in SciPy, but there's no built-in function for doing a shock response spectrum. So now in the enDAQ.calc library, you'll be able to pass it shock data or acceleration data, get a shock response spectrum. We can look into adding some other functions to like find the peak, but you kind of saw my example. The other thing in our library for the shock response spectrum, we have a function to find the equivalent half sine pulse. So you have really complex acceleration data, and maybe you just want to simplify it into, well, what is the equivalent amount of energy in just a simple half sine pulse? There's a function to give you that result. And it's we're actually giving a paper, Becker is, and a talk. That might be its own webinar and blog. It's kind of unique and nice in the sense that there's just one optimal half sine pulse per acceleration data set. If you guys have used the vibration data toolbox, what Tom is doing is he's looping through and trying out a bunch of different things and picks the one that is closest. But that means if you run it once, you'll get a completely different result if you run it again. Whereas in our function, there's just one result, no matter which time you run it. So that's a really exciting contribution to the world of data analysis and shock and vibration analysis.
Right. And is there already a vibration or FFT analysis database made for Python?
Yeah, so there's the SciPy Welch function, which I linked to, and you see it's very similar to the MATLAB version. We will have, we're going to basically wrap up some of this into our function, so you don't have to kind of, in the SciPy one, you have to explicitly say what your sample rate is, and then you have to kind of merge the results back into a data frame if you want to plot it. But that's already available in scipy.signal. There's also a bunch of FFT libraries. I'm showing the example from scipy.fft. There's also FFTW, which is going to be equivalent to the one that MATLAB uses. So those would be the ones I'd recommend for power spectral density, scipy.welch or scipy.signal.welch. And then for FFTs, I think I'd go to FFTW.
Time for a few more.
Yeah.
Okay. So can Will the enDAQ library be backward compatible to older versions of Python?
David, do you want to answer that? I think it will be in Python 3. It won't work in Python 2.7, but I don't think there's any reason why it can't work in Python 3.7 versus 3.8 versus 3.6. Am I right, David?
I'll have to double check. I definitely it's Python 3 only. We are at enDAQ, we've stayed with Python 2 for other projects for far too long. We're definitely trying to get out from under it. I would have to double check about what versions of Python 3, but certainly I think that we were saying like 3.5 or 3.6 on.
Okay.
There were some grammatical changes, syntax changes since then.
Yeah, that's a good question. Remember though, if you go to just that Anaconda individual or the individual edition, I think they let you, again, it's free. And I think on their download page, here we go, you can get, I don't know where their download page is, you can get the most recent version very easily. So, but it's a good question.
Can random shock vibration from HASS be analyzed?
Oh, halt, Haas, what is that? Oh, yes. In our example, we loaded in data. I don't even know what the source was, but they don't need to be coming from our devices. The HASS, or what are those accelerated life testing machines? It's just acceleration data. So yeah, it will be the same analysis steps as what I just went through. One thing we do need to add in our upcoming library is a way to batch through. So if you have a set from those accelerated life testing machines, they test at different settings and intensity over time. And so you may benefit from segmenting your file and saying, okay, I want to see a power spectral density of the first minute, then the second minute, third minute, and I want to, segment it. So we'll have some functionality to help do that in one of our modules as well. But yeah, I don't see why you can't.
And can we share any explanatory slides for PSD analysis of vibration data from a CSV file in Python?
Yeah, we can look to do a very explicit deeper dive on that. What you can follow along with this Colab link, and it's really, here is my function. My input of it was just, if you remember, the acceleration data, X, Y, Z, and time. And then here's my function. I'm passing in the acceleration data. Oh, wait, that's the PSD. Here it is. And then here's the output. Once I have that function defined, I just pass in my acceleration data set and I get the output of a power spectral density in units of the unit squared per hertz. So we're wrapping this into one function. I forget what it's going to be, Becker, but it will be enDAQ.calc.psd, maybe, I'm not sure, maybe .welch. And so you would equivalent, you just change this part to that, and you never have to define this function. But I think this example already is kind of giving you going from a CSV of acceleration data into a CSV of the power spectral density. Remember, I saved it here, dfpsd.csv to CSV, and now it's saved, and then I plotted it. So it's really just those 3 lines of code, or those 3 cells.
So that concludes all of our questions.
Okay, good. Well, we went a little long, but I think that was good. We're going to launch a survey, right, Tina? And one of the questions I have, and we have a number of questions we're really interested in the answers to, but one is if you guys want us to do some deeper dives, and maybe that's a good one of generating power spectral densities in Python. So I'm curious to see your feedback there, but thank you, everyone. I'll hand it back to Tina. Look forward to talking to you all soon.
Well, thank you everyone for attending today and for all your great questions. We hope you found this webinar helpful and informative and that you're ready to experiment with and use Python. If you have any other questions or think of something later, don't hesitate to contact us. We'll send out an email in the next few days with a recording of this webinar, a link to the slides, and also some links to some helpful resources. Once we close the webinar, as Steve just said, a survey will launch. Like I said in the beginning, we'd love to have your feedback on this webinar so we can improve our content and ensure that we're providing relevant resources that can help you with your analysis. And just to remind you, we're going to be running a follow-up webinar next month on October 13th on our new open source Python library to make data analysis even easier in Python. You can sign up for our webinar notifications and we'll contact you with the link to register. Should be another good one and hopefully we'll see you there. Again, from all of us at enDAQ, thank you so much for joining us today. We really appreciate your time. Take care. Bye.